In this lecture, we'll be introducing the concept of equilibrium. And this is covering material that is in chapter 17 of the textbook. The title slide, this is from a different source, and I think it's a good summary of what we're going to go over today, and that's dealing with reaction quotient, which is capital Q, and equilibrium constant, which is capital K, and the relationship between one another. Okay, at equilibrium, Q, the reaction quotient, is equal to K, the equilibrium constant. Okay, you can use the reaction quotient at any other point other than when it's at equilibrium to tell which direction the reaction will go, either forwards or backwards. So when Q is smaller than K, that means the reactants are larger than they are at equilibrium. The products are less than at equilibrium, so the reaction is going to move forward, go from reactants to products, at least how the equation's written. Okay. And when Q is larger than K, the opposite will happen. Products actually go to reactants, so the reverse reaction happens in that case. Right, and they do this so that they move towards equilibrium so that Q ends up equaling K. Okay, so just refresh ourselves. Last lecture, we talked about when a reaction is spontaneous, and that was when we have this case with Gibbs free energy. When the change in free energy is negative, that's when the reaction's spontaneous. And we went through the relationship of the free energy to enthalpy, entropy, and temperature. And we introduced that equation. We talked a little bit about, at the end of the lecture, the thermodynamics of biology and some intermolecular forces from chapter 12. Okay, today we're going to introduce equilibrium constant, reaction quotient, and then equilibrium with respect to pressure. And how do we use reaction quotient and equilibrium constant to determine the reaction direction. So this is chapter 17, starting with section 1 of chapter 17. What is equilibrium? All right. Well, what equilibrium means, in a sense, is that it really means that you have the forward and reverse reactions of a chemical reaction going at the same time, and the rates are equal. The forward rate is equal to the reverse rate. Okay. Pretty much all reactions are reversible under suitable conditions. Okay. We haven't really been considering that in this class up until now. We've just been sort of showing a reaction occurring in one direction, but most often is the case in real-world situations. Reactions can be forward and reverse and are in equilibrium. Okay. And again, equilibrium means that the forward rate of a reaction is equal to the reverse rate. So this chemical equilibrium really is a dynamic state. The reactions are still occurring, the forward and reverse. It just doesn't look like that from the outside because the concentrations of reactants and products stay the same because the forward and reverse rates are equal. Now, if we use a plot to plot rate versus time for reactions, right? You might have a case if you have really only reactants available. What's going to happen is that's going to do the forward rate, and the reverse rate is going to be very, very low, right? Because you don't have any products yet to go in reverse. So as that reaction goes forward and you form products, the forward rate's going to slow down a little bit, and the reverse rate's going to pick up. And that's because you're going to be forming products. those products now can react and go the reverse direction back into reactants. Okay, and so eventually these two rates will equal out. Okay, and they'll reach a point where they're the same, and then they move along this horizontal line. And in this purple case here is where we would reach equilibrium. The forward and reverse rates are equal. And you can also plot the amount of products and reactants versus time, and you'd get a very similar plot, right? If you start with all reactants and no products, right, the reactants will slowly go down because the forward rate's depleting them. Products will slowly build up because the forward rate is producing those products. But then after a certain point, the concentrations or amounts of the reactants and products won't change. Okay, and again, that's the equilibrium, where equilibrium is reached. Okay. Just looking at this in a picture form, if we have N2O4 going to 2NO2, the NO2 is colored and N2O4 is not. So when we start this out, you can see that inside that reaction vessel, it's a slight color because there might be a little bit of NO2 in there. But after time, right, this reaction will move more towards the product NO2, and then you reach a certain point where the equilibrium has been reached and it no longer gets any darker. A major part of equilibrium and dealing with equilibrium is the equilibrium constant. And this tells us exactly how much balance between reactants and products for a given reaction there'll be. And I should mention too, because all these reactions can be written in both directions, when I say reactants and products, I'm really referring to how the reaction is written. Okay, so please note that when I say reactants, it means the species that are on the left side. Products means the species that's on the right side. Sort of arbitrary, right? Because we could write that reaction in the opposite direction, and then those terms would be flipped. Okay, and it's going in both directions, so that term is a little misleading, I guess. But it's dependent on how we're writing this chemical equation. Okay, so here we have N2O4 as our reactant and NO2 as our product. Okay. At equilibrium, remember the rate forward equals the rate reverse. And we haven't talked about this yet. This is in chapter 16, which we've sort of skipped. We'll come back to later in the quarter. But rates can be written as a rate constant, which is a lowercase k, times the concentration of your, in this case, if we want to look at the forward rate of this reaction, it'd be times the concentration of our reactant. Okay? And so at equilibrium, the rate of the reverse reaction is equal to that. And so if we wanted to write that rate, it'd be little k reverse, so rate constant of the reverse reaction, times the concentration of NO2, the product, and we would square that because there is a coefficient of 2 here. Again, you don't need to know that yet. We'll talk about that in chapter 16. Okay. So you can rearrange this mathematically to get the rate constants on one side and the concentrations on the other. And so when we do that, these rate constants become what is known as the equilibrium constant. Okay. That equilibrium constant, capital K, is equal to the forward rate constant divided by the reverse rate constant. Right. You can, and that in itself probably not very useful for us, but what is the fact that you can relate the equilibrium constant to the concentrations. So it's always going to be the concentrations of the products divided by concentrations of the reactants. And you'll notice too, you have to put in that coefficient, whatever the coefficient is in the balanced chemical equation, it gets raised, the concentration of that gets raised to that power in the equilibrium constant expression. So K reflects a particular ratio of product concentrations to reactant concentrations for a given reaction at a given set of conditions. And therefore, K really indicates the extent of a reaction, or how far a reaction will proceed towards the products at a given temperature. A small K value would indicate that the reaction doesn't really go forward very much before it reaches equilibrium. So in a sense, it favors the reactants for small K. Large K is the opposite. It tells you that by the time the reaction reaches equilibrium, there's much more product and very little reactant remaining. Okay, so that reaction favors the products when K is large. Okay. Graphically or pictorially, we can look at this figure from our text. Okay, K here, we can write this just general expression here for these. So K is going to be products over reactants. Okay? And here we have one product molecule, and if you count those up, which no one really should, but there would be 49 reactants. So product 1 divided by 49 reactants, K in this case would be 0.02. Okay, so that's very, very small. All right, and you can see that for a small equilibrium constant, that favors the reactants. If we have the opposite case, when we have one reactant left at equilibrium and 49 products, right, that K expression becomes 49 divided by 1, or 49, so a larger value for K, and you can see that this reaction at equilibrium favors the products. When it's something, a 50-50 mixture at equilibrium, this is a case where you'd have a equilibrium constant of 1. Okay, so that was the equilibrium constant. Now moving on to the reaction quotient. And luckily for us, the reaction quotient mathematically is written the same exact way an equilibrium constant would be written. Okay. The only difference is now we're using the symbol Q. Okay. So for a generic reaction here, A plus B goes to C plus D, and the lowercase letters are the coefficients in the balanced chemical equation. We can write a reaction quotient like this. Okay, it's the products divided by the reactants. So it'd be the concentration of C raised to the C power times the concentration of D raised to the little d power. Okay, so you'll notice that we're multiplying those together. Okay, in the chemical equation, we put plus signs, but when we're calculating a reaction quotient or equilibrium constant, we multiply them. Okay, so products divided by the reactants. So the reactant would be concentration of A to the little a power times concentration of B to the little b power. And again, when Q equals K, that's a case when we have reached equilibrium. Okay, for a particular system and temperature, the same equilibrium state is going to be obtained regardless of starting concentrations. Okay, so you can start with as much reactants or as much products as you want, but at a given temperature, the system will reach the same end concentrations. Right. the value of Q indicates how close the reaction is to equilibrium at any given point in time and which direction it has to go to reach that equilibrium. So if we look at the change in Q during that N2O4 NO2 reaction, okay, when Q is not equal to K, right, that's the case when if we're plotting the amounts of NO2 and N2O4, right, when those plots are, curves are changing, this is a case where Q does not equal K. And then when those have no more change left in them and they reach those horizontal lines, that's when Q equals K. Okay. So heterogeneous equilibrium, what does that mean? Heterogeneous just means that you have reactants and products that are in different phases. So in the case here, we have calcium carbonate, which is a solid, going to calcium oxide, which is again a solid, plus CO2 gas. Okay, a pure solid or a pure liquid will always have the same concentration. Okay, so it's makes this simpler for us because those pure solids or pure liquids aren't changing in concentration. We don't have to consider them when we're calculating reaction quotient or equilibrium constants. Okay, so for the above reaction, right, the only thing that would be gas and thus changing in concentration would be CO2. So our reaction quotient or equilibrium constant in this case becomes very simple. It becomes just the concentration of CO2. And this figure just kind of shows this graphically. In this side we have more calcium carbonate than calcium oxide. This side we have more calcium oxide than calcium carbonate. But at the same temperature, we're going to end up with the same carbon dioxide concentration because both have the same equilibrium constant. Okay, so let's try a sample problem with this, writing the reaction quotient from balanced chemical equations. So the first reaction we have here is N2O5 going to NO2 plus O2. And I should mention the double-sided arrows did not turn out very well on these slides, so that's why you see this kind of weird added double-headed arrow. Normally they should look something like this. But yeah, they for whatever reason didn't come out on the slides, so I had to add these extra ones in. Okay, so if we want to write the reaction quotient for the first one, well, first we're going to have to balance this equation. Let's see, where should we start? Let's go. There are 4 oxygens on this side and 5 on the other side. That doesn't help. If we added a 2, let's just try adding a 2 in front of NO2 to balance nitrogens. Okay, then we're going to have 2 times 2, 4 oxygens plus 2, so that's 6 oxygens, and there's 5 over here, so that's still not really good. Turns out we have to add a 2 in front of NO2, N2O5, and this becomes a 4. And when we do that, we just need a 1 for the O2. Okay, so that's balanced. So our reaction quotient for A becomes concentration of NO2 to the 4th power, multiply the concentration of O2 okay, by the first power, divided by the reactants, which in this case is only N2O5, and that is to the second power. Okay, so that's for A. Let's try B. Okay, we have to balance this again, and you can go through this and balance it. You should get 2's for everything except H2. Now, right in this again, it's products over reactants, so NaOH squared times the concentration of H2 to the first power divided by reactants, so Na. Oh, and I've already messed up because pure liquids and pure solids do not factor into this equation, right? So we have a pure solid and a pure liquid, right? So we don't actually need anything for the reactants in this case. Okay. So always important to remember to check that. Okay. And finally, our last reaction, if we're going to balance this, to balance it, we would need 5 O2s, 3 CO2s, and 4 H2Os. And when you're doing that, if you just balance, carbon first, you would be able to, and then hydrogen. That's how you would come to that answer. Okay. Right, so then again, the reaction quotient, products over reactants. So products would be CO2 cubed times H2O to the fourth. Again, that's because they're both gases. If H2O was a liquid there, we'd have to omit it. And the reactants, C3H8 times O2 to the fifth power. Okay. So for an overall reaction that is the sum of two or more individual reactions, how do we use K and Q, and how do we relate the K or the Q for the individual reactions to the overall? Well, it turns out you multiply them by one another. Right, so we multiply, if we had, doesn't really matter how many, but, let's say we have 3 reactions in this step. The overall reaction quotient or equilibrium constant would just be the product of all of the individual steps. The form of Q and K depend on the direction in which the balanced equation is written. Again, sort of mentioned that earlier. If you want to flip the direction how the equation is written, the reaction quotient or equilibrium constant of the reverse reaction would just be 1 over the reaction quotient or equilibrium constant of the forward direction. Okay, so you would just flip the fraction. What's considered a product in one direction would be considered a reactant in the other direction. So you'd have to switch how the fraction is written. Okay. The coefficients of a balanced chemical equation are multiplied by a common factor. So in the case where you have you're trying to manipulate a certain equation to get it to cancel out in a series of equations, and you have to multiply through by a certain factor, like 2, let's say, well, then you would take that reaction quotient that you would have written for that reaction that you need to multiply through by 2, and you'd have to raise it to that power, right? So in this case, if we multiplied through by 2, we'd have to raise it to the second power. So let's try a practice question using this sort of concept. We have a chemist that wants to find the Kc, the equilibrium constant for the fallen reaction. Okay, so we have 2NH3 plus 3I2 in equilibrium with 6HI plus N2. Okay, all gases. Don't know the equilibrium constant for this reaction. We know the equilibrium constant for 2 other reactions shown here. Okay, so we need to, sort of similar to Hess's law in chapter 6 with enthalpies, we need to arrange these 2 equations to give us our target equation. Okay, so we need to rewrite these equations to equal the target. So if you look at what's a product and what's a reactant, or what's on the left side, what's on the right side, in the first equation, N2's on the left side here, it needs to be on the right side. So we're going to have to reverse this one. So we need to reverse that to two NH3s go to N2 plus 3H2. And remember when we do that, that equilibrium constant is going to be the inverse. So it's going to be 1 over 0.343. Okay, so that's our new expression for that reaction and equilibrium constant. The next equation, if you look at the second one, the stoichiometry is just going to be a little bit wrong. I2, we're going to need to have 3 of those. So what we're going to have to do is multiply through by 3. And when we do that, remember, the equilibrium expression gets raised to that power. So it'd be 54 to the 3rd power. Okay, so then the overall equilibrium constant is just going to be, and I probably should just work through this, make sure it adds up to what it should. 3H2, those are going to cancel on both sides. What we're going to be left with is 2NH3 plus 3I2 goes to 6HI plus N2. So those equal each other. Okay, so now we can take the equilibrium constant for each step in this reaction and we multiply them by each other. Okay, so the first reaction would be 1 divided by 0.343, and then we'd multiply that by the second, which is 54 to the 3rd power. And when we do that, we get something like 4.59 times 10 to the 5th. So a pretty large number. And a lot of times in this class, I'll leave this plan out just for you to look at if you're looking through these notes after the fact, after class, or during class. It just gives you a idea of how the problem is going to be solved. Right, so in summary, we have different ways of expressing Q and K. And I like this table because it shows you really simply have all the information kind of in the same spot here. So for our generic reference reaction, A goes to B, right, A going to B, we have the equilibrium constant, and reaction quotient would just be the concentration of B over A. Okay. And again, equilibrium constant, those would be equilibrium concentrations. Q is at any other point. If we flip that over, if we flip that reaction over, right, then the new equilibrium constant or reaction quotient is just going to be 1 over the original, okay, or A over B. Now, if you have a reaction as a sum of 2 steps, so here we write A to C and then C to B, so that would be a 2-step process to get that same thing. What do we do? Well, we'd have 2 separate reaction quotients or equilibrium constants for each of those. Okay, can be written that way. The overall, again, is just going to be 1 multiplied by the second step. When we do that, if you did that, you could see that C is going to cancel out, and we're just going to be left with B over A, which is the same as what we had when it was just a single step. So that is good. It's agrees. Okay. And when you have to multiply coefficients through, those equilibrium constant and reaction quotient get raised to that power. And remember, if you have a reaction with pure solid or liquid, those do not factor in. Okay. So this third section of chapter 17 is dealing with the equilibrium constant, but in terms of pressure. Okay. So K for a reaction may be expressed using partial pressures of gas instead of using concentrations. And when we write these out, they're written out in the same way, except instead of concentration, we're using partial pressures, and those are written as capital P subscript of whatever gas that you're talking about. So the partial pressure here of nitrogen or nitrogen dioxide, NO2, we write that as P subscript NO2. Right. So in this reaction, 2NO plus O2 goes to 2NO2. Our reaction quotient, right, if we were writing Q sub C, right, reaction quotient based on concentration, it would be the concentration of our product divided by the concentration of our reactants. But Q sub P is going to be the same pattern, but we're using partial pressure of NO2 divided by partial pressure of our reactants. Okay, and again, you're raising that to whatever the coefficient, the power is going to be whatever that coefficient is in the balanced equation. Okay, so Q sub P and Q sub C, it's the same basic math to find them. You're using pressures, the other you're using concentrations. Okay, the relationship between the two is shown here. K sub P is equal to K sub C times the gas constant times temperature raised to the delta N power, which is the change in number of moles of gas from one side to the other. Okay. And you can see that if the number of moles of gas doesn't change in the reaction, that delta N value is going to be 0, and when that happens, RT to the 0 is just going to be 1. So K sub P equals K sub C. So let's try a quick practice question with this. Okay, if we have ammonium hydrosulfide decomposes to ammonium and hydrogen sulfide gases, find K sub C for the decomposition reaction given here. And it gives us a K sub P value. Okay. So we know our K sub P. So to convert between the two, we have to first determine the change in moles of gas from the balanced chemical equation. And then we have our gas constant and our temperature given here. So the delta N of our gas, we have 2 moles of gas, so there'd be 1 and 1. So that'd be 2 moles of gas as products, and we'd minus the number of moles of gas as reactants, but as you can see, NH4SH is a solid, so there's 0 moles on the left side of the equation. So delta N is going to be a plus 2. Okay, we have R, we have K sub P. Temperature is given as 218 degrees Celsius. Okay, we add 273 to that to get the temperature in Kelvin, which is 491. Okay, now we can use our equation. Okay, remember again, our equation is K sub P equals K sub C times RT to the delta N power. Okay. So if we rearrange this to solve for K sub C, that would be K sub P divided by RT to the delta N. So let's plug these in now. 0.19 is K sub P. R is 0.0821 liters atmospheres divided by mole Kelvin. And temperature is 491 Kelvin. And then we would raise that to the second power. Okay, when we do all that math, should be getting a number, fairly small number, 0.000117. Okay. So now, probably one of the more important sections in this chapter, how do we use Q, and how do we use it to determine which direction a reaction will go? Okay, so the value of Q is indicating the direction in which the reaction has to proceed to reach equilibrium. And as we've mentioned before on the title slide, if Q is less than K, the reactants must decrease and the products increase. So the reaction has to go forward. Okay, if Q is bigger than K, the reactants must increase and the products must decrease. So the reaction is actually going to go backwards. Right? When Q equals K, that's when we have that system's at equilibrium and no further net change takes place. The forward and reverse reactions are still occurring, but they're at the same rate, so no net change takes place. Okay. And again, this was very similar to what we saw in the title slide, showing the direction reactions have to take place with the relative Q relative to K. So let's try a practice problem using this principle. We have the reaction A going to B. Okay. The equilibrium mixture at 175 degrees Celsius. We have A concentration of 2.8 times 10 to the minus 4 molar, and B is at a concentration of 1.2 times 10 to the minus 4. Okay, the molecular scenes below represent mixtures at various times during runs of this reaction. Okay, A is red, B is blue. Okay, and in each case of each of these four cases, we have to determine, does this reaction progress to the right or the left of this, right, to the right B or to the left A, or not at all? Is it already at equilibrium? Okay, so what do we need to do here? Well, we need to figure out, well, let's first, I'll draw our generic reactions, pretty simple. A is equilibrium with B. Okay. We need to find first what the equilibrium constant is. Okay, so we can't compare Q's until we know what K is. So we're given the fact at equilibrium, concentration of A was 2.8 times 10 to the negative 4 molar, and the concentration of B was 1.2 times 10 to the minus 4 molar. Okay. So what would our expression for K be? Well, K is just going to be equal to products, which would be B, over reactants, which is A, and when you do that, we get 0.429 for our equilibrium constant. Okay. So now we have something to compare to, and now we need to calculate Q for all four of these cases. So for case number 1, Q, right, remember A is blue and B is, excuse me, A is actually red and B is blue. Okay, so Q for number 1, we'd have, again, it's products or right side over reactants or left side, so B over A. So if you count those up, there are 1, 2, 3, 4, 5, 6, 7, 8. 8 B's and 2 A's. So our Q in this case is 4. Q is bigger than K, right? So Q is bigger than K for this case because K is 0.429. So what does that mean? That means if you look at Q, right, that's products over reactants. If it's bigger than K, that means we have too much products. So we need to go backwards. So the reaction is actually going to go in the direction of B to A. So you can think of this, right, for Q, the expression Q, it's going to be products over reactants. So hopefully you can kind of see this, but just generically, Q is products over reactants. If you want to get to a larger Q value, you're going to have to increase your products. Okay. If you want to get to a smaller Q value, you're going to have to increase your reactants, so go in the reverse direction. So that's the case we had here. Q is 4, and we want it to get to 0.429, so it has to get smaller. So you have to increase your reactants or go in the reverse direction. Okay, so let's look at condition 2. Q is going to be 3 over 1, 2, 3, 4, 5, 6, 7. 3 over 7, which is, when you do that math, 0.429. So this is a case where Q equals K. So we are at equilibrium. So the reaction, there are no changes in the concentrations of these. Okay. Condition 3, Q is going to be 4 blues over 6. That is 0.667. That means Q again is larger than K. So we are going to go in the direction of B to A, so reverse. And then finally, Q would be equal to 2 blues over 8 reds. So 2 over 8. That fraction equals 0.25. That means Q is smaller than K. When Q is smaller than K, that means you still have your products are smaller than they should be, and so you need to go in the forward direction. One last sample problem. Okay. For the reaction N2O4 to 2NO2, our K sub C is 0.21 at 100 degrees Celsius. At a point during the reaction, the concentration of N2O4 is 0.12 molar, and the concentration of NO2 is 0.55 molar. Is the reaction at equilibrium? And if not, which direction is it progressing? So our basic plan for this is we need to write the expression for Q and find its value by substituting in the concentrations we're given, and then we compare that to the value for K that we're given. Okay, so N2O4, again, we're given that as 0.12 molar. The concentration of NO2 we're given as 0.55. What is our expression? So our expression again is products. So that would be concentration of NO2. We have to square it because there's a 2 in that chemical equation coefficient, divided by reactants, which would be N2O4. Now we can plug things in. So this would be 0.55 squared divided by 0.12, which would be 2.52. Okay. K is 0.21. That's what we're given up here. So we are at a case where Q, at these concentrations, Q is going to be bigger than K. Right, so what does that mean? Well, remember, if we're looking at the expression for Q, if it's bigger, that means the products, the things on top of that fraction, that ratio, they're going to be bigger than they should be. So if the products are more than they should be, this reaction is going to proceed towards reactants. In other words, it's going to go backwards. So as we have it written, it would go backwards. Okay, so next time we'll continue on with Chapter 17 and learn steps to solve equilibrium problems, and how to utilize reaction tables, or some of you might know them as ICE tables.